Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. Today we are going to discuss about the module Vacuum-based thin film deposition techniques from the paper Electronics. So students, let us see what we are going to learn in this module. First, we will discuss about the thin film growth process. Second, the sputtering deposition, that is DC and RF, will be discussed. Third, thermal evaporation technique will be discussed. Lastly, we will discuss about the pulsed laser deposition technique. So students, let us start with a basic introduction about the module. Thin films, they have been used for more than 50 years in the semiconductor industry for making electronic devices, optical coatings, decorative parts, etc. Although the thin film technology is well established, but it is still being developed on a daily basis to meet the current requirements. So the classification between the thick and the thin film cannot be made on the basis of the thickness, but it is the deposition technique that actually differentiates them. So a thin film is defined as a low dimensional material which is created by condensing one by one atomic molecular ionic species of matter on a substrate. On the other hand, a thick film is defined as a low dimensional material which is created by thinning a 3D material or application of dispersion or paste of a material directly on the substrate, followed by drying and heating process at high temperatures. Thin film growth processes. Any thin film deposition process involves three main steps. First, the production of the appropriate atomic, molecular, or ionic species. Second, the transport of these species to the substrate through a medium. And third one is the condensation on the substrate either directly or via a chemical and or electrochemical reaction to form a solid deposit. So students, thin film of a material which is created by any deposition technique starts with a random nucleation of atomic, molecular, ionic species at the substrate, followed by the growth process, subsequently filling the network structure to form a continuous film. The nucleation and the growth stage depends on the deposition conditions such as substrate chemistry, growth temperature, processing ambient and growth rate, and can be modified significantly by electron or ion bombardment. Processing conditions influences the basic properties of the deposited thin film, such as composition, crystalline phase and orientation, thickness and microstructure. Crystallization of the thin film occurs during the coalescence stage, and the crystallographic orientation and grain size depends upon the nucleation density. which in turn is determined by the surface mobility, processing time, thermal treatment, and kinetic energy of the arriving species. So, thin film deposition techniques can be broadly categorized into two classifications depending on the initial individual state of atomic, molecular, ionic species. The number one is liquid phase deposition and second is vapor phase deposition. Vapor phase deposition is further classified into chemical vapor deposition, thermal evaporation, molecular beam epitaxy, pulsed laser deposition, and sputtering. So let us now study the details of these techniques in the following sections. Slide 6. Let us first discuss about the sputtering, DC or RF. Sputtering is a physical process where atoms in a solid target material are ejected into the gas phase due to bombardment of the material surface by energetic ions. Sputtering of surface atoms has been known since 1852. When Grove observed the process during investigations of plasma discharges, and subsequently it was soon recognized that sputtering process can be applied for the deposition of thin films. Sputtering process is driven by the momentum exchange between the energetic ions and atoms in the target material due to collisions. So the process can be thought of as the atomic billiards, with the iron cue ball striking a large cluster of closely packed atoms, billiard balls. Although the first collision pushes the atoms deeper into the cluster, subsequent collisions results in the ejection of some of the atoms near the target surface being ejected away from the cluster. The number of atoms ejected from the target surface per incident ion is called as the sputter yield, and it is an important measure of the efficiency of the sputtering process. So this shows the schematic of the basic sputtering process. Now students, so here the sputter yields depends on the energy of the incident ions, mass of the ions and target atoms, and binding energy of the atoms in the solid. So in practice, a variety of modification in sputtering technique are used to influence the plasma properties, especially ion density, to achieve an optimum growth kinetics, including usage of direct current DC, alternating current AC at radio frequency, utilization of magnetic fields, and application of a bias voltage to the target. Advantages of sputter deposition. Number 1. Elements, alloys, and compounds can be sputtered and deposited. Secondly, the sputtering target provides a stable, long-lived vaporization source. Thirdly, in some configurations, reactive deposition can be easily accomplished using reactive gases, species that are activated in plasma. Next, the source and the substrate can be spaced close together. Next is that the sputter deposition chamber can have a small volume. Disadvantages of sputter deposition are: number 1, sputtering rates are low as compared to those that can be attained in thermal evaporation. Second, sputtering targets are often expensive and material use may be poor. Thirdly, most of the energy incident on the target becomes heat, which must be removed. Next disadvantage is that in reactive sputter deposition, the gas composition must be carefully controlled to prevent the poisoning the sputtering target. Let us now discuss about a DC sputtering. DC diode sputtering process is a simple technique for the deposition of metallic thin films. A sufficiently large electric potential, for example around 1500 volts, is applied between two closely spaced electrodes. The cathode consists of a target material to be sputtered, whereas the anode is grounded with the wall of the discharge or deposition chamber. So, applied electric field DC between the electrodes causes the emission of electrons from the cathode. These electrons gains kinetic energy and they move towards the anode. So in the path, there is a finite probability that these electrons will collide with the inert gas atoms, generally argon is used, and liberate other electrons called as secondary electrons. So if the energy of the accelerated electrons is sufficiently large, ionization of more and more gas atoms occurs and plasma is struck inside the chamber. The positive argon ions in the plasma are accelerated towards the cathode and they eject the target atoms due to the transfer of momentum, which gets deposited on the substrate to form a thin film. So the major drawback of DC sputtering is that an insulating target will not work because of the accumulation of surface charge of positive ions on the front surface of the target. This prevents any further ion bombardment and immediately stops the sputtering process. The problem of undesirable positive charge buildup, it is being overcome using several methods, such as simultaneous bombardment of the insulator target with both an ion beam and an electron beam, placing a metal grid on the surface of the target. However, these approaches were suitable for the etching of the insulators but not for the deposition of the thin film because of the contamination problem. This drawback has been successfully overcome using RF sputtering, which will be explained in the next section. Let us now discuss about the RF sputtering. In an alternating electric field, electrons oscillate to and fro, and during this motion they collide with other atoms. So the ordered motion changes to random motion due to the collisions. The energy of electrons increases sufficiently to produce the ionization collision, which further releases more electrons as shown in this figure. So the high voltage that are essential in DC sputtering for the generation of secondary electrons to sustain the discharge are not required in RF sputtering. The electrons in the plasma will have sufficient energy to directly ionize the gas atoms, reducing the dependence on the secondary generation of electrons at the cathode. So, at an operating frequency of 13.56 MHz, the ions in the plasma can no longer move quickly enough to offset the changing field, due to which only a little accumulation of positive ions occur during the portion of the cycle in which the target electrode is acting as the cathode. So, however, due to high mobility of electrons, the electron current in the target surface is initially much higher than the ion current. This results in a fixed negative DC bias on the target with respect to the plasma. So the value of the bias potential is close to half of the peak-to-peak RF voltage on the target surface. The positive ions from the plasma are accelerated towards the target essentially by the bias potential VB rather than the RF potential, and bombard the target surface with the energy of the order of VB electron volts to sputter out the atoms. Advantages of RF sputtering are: it works well with insulating targets, high efficiency, easier to keep plasma going, can operate at lower argon pressures, fewer gas collisions, more line of sight deposition. Let us now discuss about thermal evaporation. In thermal evaporation, the source material is heated in high vacuum, 10 to the power minus 6 torr, to the vaporization temperature, which condenses to on the substrate after passing through the vacuum and forms a thin film at the substrate. The simplest evaporation sources are electrically heated spiral wires or foils in thermal contact with the material to be evaporated. The refractory metals like tungsten, W, molybdenum, Mo, and tantalum, Ta, they are widely used to make the evaporation source, that is the boat, because they have a low vapor pressure at the evaporation temperature and low reactivity with the evaporant. So one can also decrease the reactivity between the source and evaporant by a ceramic coating. The crucibles of certain oxides such as boron nitride and carbon could also be used as an evaporation source when heated by refractory metal wires or foils. So students, this technique is not suitable for the elemental materials, that is for metallization. It is mostly suited for metallization or catalyst deposition, because the higher the melting point of oxide materials and large temperature difference in the individual components of multi-component materials poses a big problem of inhomogeneity and non-stoichiometry. So this figure shows a schematic of thermal evaporation system. Let us now discuss about the pulsed laser deposition, PLD. So it is a typical technique for the preparation of thin films of complex stoichiometry, well-controlled interfaces or multi-layered structures. In PLD, laser shots of nanoseconds of the intense laser with specific wavelength and high energy. They are focused on the target of the material to be used for the deposition. So the energy of the laser should be high enough so that it can ablate the target material. The deposition of the film can be performed under high vacuum conditions. However, responsive background gases such as oxygen for the preparation of oxide films or nitrogen for nitride films could also be used to maintain the required stoichiometry. An inert background gas such as argon can also be utilized for the deposition of thin films using PLD. When high intensity laser is made to irradiate the target, it ablates the material, which leads to the development of a plume, which spreads in a flow perpendicular to the surface and is collected on an appropriate substrate. The full PLD process can be portrayed by 5 stages, which are as follows. Number 1, light absorption in the solid. Second, one-dimensional plume expansion of the ablated material during laser irradiation. Number 3, free three-dimensional expansion into vacuum or a dilute background gas. Number 4, slowing down and stopping of the plume in a background gas. And lastly, the collection of ablated atoms on a substrate and subsequent film growth. So this figure shows the schematic of the pulsed laser deposition system. The deposition of thin films can be controlled by varying a few parameters such as pressure, substrate temperature, background gas, target substrate distance, etc. So students, let us summarize what we have learned in this module. First, we discussed in detail about the thin film growth process. Secondly, we discussed about the DC and RF sputtering deposition techniques and their advantages and disadvantages. Thirdly, we discussed about the principle of working of DC and RF. Next, we discussed about the thermal evaporation. Lastly, we discussed about the pulsed laser deposition technique. Thank you.